going to actually look at a labeling function notebook and then actually walk through a real application and show you some broad ways to think about writing labeling functions. This is our competition setting, so I'm not saying like keep things secret or like, you know, adversarially inform your neighbors of the wrong thing. In fact, I think sharing information is actually interesting because we're really kind of curious about that setting where you guys are probably gonna have labeling functions that do similar-ish things, right? So if you guys can go ahead and open up this Workshop 2A PubMed Writing Labeling Functions notebook. And I should say for people who, like, you should keep that, as I said, the API notebook open in the background, but we'll have Kevin and Abraham and Alex and, people will be available to answer sort of programming questions as needed. So as we get into the depths of this, please, ask them questions. Okay. So you'll notice you can ignore this for today, but there's a little setup that goes on behind the scenes that basically says, I want to plug into a specific database to use a specific application. So by default, everybody's set to this chemical disease relation task, so you can ignore it. But when we get in tomorrow, we'll be changing just a single variable behind the hood to plug into the right place. So that's what that first cell means. Okay, so what we're going to do is we're going to think about writing labeling functions to very specifically predict this chemical disease relation task. And we'll walk in through some real examples to show you sort of what that actually means. But first, let's go ahead and instantiate all of our setup stuff. So just run that first cell. Notice now that the spouse, we defined a type defined by two people names. For this task, we're defining a type called chemical disease that consists of the arguments chemical and disease. So to access your candidates, instead of c.person1, person2, it's now c.chemical, c.disease. Everything else is the same.
And I assume presumably there's some invisible work that was done to make sure the chemical always comes first.
Well, yeah, so yeah, absolutely. So it doesn't necessarily come first in the sentence, right. But from the candidate object, yeah, if you access it through chemical, you'll always have it. There's no real ordering in the candidate, I guess is what I'm saying. But
okay.
So let's take a little time and define this task. The chemical disease relation was this big, if you guys are familiar, this bio-creative challenge. They run various sort of PubMed-based information extraction tasks. And what this asks you to do is to identify chemicals and diseases, ignore their mesh IDs for the moment, and identify pairs of chemical diseases where there's a causal link between the two. So in the sense that a chemical causes this disease, okay? And that's basically the gist of it. So you might think like, oh, I don't know anything about chemicals or diseases or any of that stuff. But actually, in fact, what you find reading these is usually pretty clear from the text what the intent is. So your goal here is not to, in some true, absolute world knowledge sense, know, yes, this chemical causes this disease, but it's as a human to read a sentence and say, yes, I believe this sentence expresses that this chemical causes this disease. And your task in writing labeling functions is to identify the clues that inform that decision, yes or no. And again, we'll be writing both labeling functions for true cases and labeling functions for negative cases. All right, as has been hinted several times through the day already, a lot of pre-processing went into setting this task up. We parsed a bunch of PubMed abstracts. We ran a state-of-the-art entity tagger to identify chemicals and diseases. And then we did a bunch of other cleanup to pour everything into Snorkel format. That's all also available online in a notebook if you want to walk it through from start to finish. But we won't talk about any of the nuts and bolts there today. Just know that by and large, especially if you have a nice performing tagger, the setup is pretty straightforward. If you don't have a nice performing tagger, it's a little more complicated, but it's still something you can totally do. For tomorrow's task, actually, we make the assumption that you don't have a tagger, and we just show supervision in a setting where you have much noisier candidates. Yeah.
So about the diseases, like, are they like specific proper names or like just general conditions like fever, like?
It generally runs across the map. There is some space of things like a disease, like disease alone is too general, so I believe that's excluded. But it's generally anything tagged as a disorder, assume the entities and chemicals are correct for your purposes. That's one abstraction here. I guess this is skipping ahead a little bit, but when you're writing labeling functions, it's usually less productive to write labeling functions that fix something like tagging, because you could always assume that you could just make a better tagger and that would solve the problem better than writing labeling functions. The key is to focus on that hard part, like the domain knowledge or the clues that are really difficult to, get into a model to begin with. Okay. So again, this link actually doesn't work, but I'll at the end of the day, I can show you the real advanced notebook that sets all that stuff up. We make the assumption here that you have a collection of human labeled data with true answers. Here it's super helpful that you can examine it to get an idea of what's true or false, just to know, how that's defined by the task. We also use it to compute empirical accuracies of labeling functions and give us all sort of insights to explore the data. Okay. I'm going to load this helper function here. Just says I have all of the gold true answers in the database. I'm just going to load them and assign them to this list or this matrix object or a NumPy array object. Okay. So one of the most critical things about designing labeling functions or any weakly supervised sort of application is really like exploring and interacting with your data, right? Like you need to sort of see what type of things you will be labeling. And so I'm going to launch this, and you'll see that we have this little nice viewer application. What this does is it's highlighted chemical in red, disease in blue. You'll see that there are some other sort of grayed or like not highlighted stuff. Here at the bottom, you have some tools to interact with stuff. You can ignore these for now, but this is if you wanted to label a bunch of data by hand, you could totally do that. I don't recommend it. As you guys are here, you're probably well associated with all the fun of hand labeling data, but you can walk through all of the candidates in a sentence, right? And the takeaway here is that there are frequently multiple candidates per sentence. So this says, is this Cushing syndrome treated on a long-term basis with ketoconazole? And then, of course, the other one is that developed sustained hypertension. This task asks you to distinguish drugs used to treat a disease and drugs that cause a disease, right? So keep that in mind when you see treatment, like potentially that's something that gives you a clue that this doesn't causally cause this disease. These two buttons interact with the candidates, and then these up and down arrows let you walk through different sentences and again explore different stuff. So like things like nitroprusside for induced hypertension. Induced seems like it perhaps is a clue that you might want to think about when writing these things, writing labeling functions, and so forth and so forth. This is one way to view the data. Another way that I find useful is to run this little visualization tool. And basically this says I want only one candidate per sentence, and I just want to look through, in this case I only look through 5, but I just wanted to look through multiple examples to explore my labeled data and see how things are labeled. Here I'm saying show me only true cases. And then I can change this and say show me only negative cases, right? And so this gives you, I would suggest taking a little time to look this over before you really dive into labeling functions to sort of build an intuition for correlated signal with these two classes. And again, if you want to look at more, Just change this number, this n max number, and you can generate a larger sample up to, the 100 or whatever total we have available for you guys to look at. Okay. This covers again what we talked about a little earlier, which is just our formal metrics. Coverage is just the number of candidates labeled or touched or voted on by a labeling function. And then precision recall F1 are just the standard, again, information retrieval metrics. Okay. I think I've followed everything.
So question.
Yeah.
Since, as we were talking about it before, this first bit, the labeling functions are to target precision, and the final model, going from the probabilistic labels to the model farthest on the right, are really to boost up the recall. Why are we focusing on F1 here rather than a different F measure with a different beta value?
You can absolutely use a different F measure with a different beta value. So
Okay.
this is just for like I said, whatever metric's most appropriate for your use case. So
Okay.
we'll say later, but you do see boosts in recall, but sometimes you see boosts in precision as well, right? And so your overall, all your numbers can go up. So like in a clinical application that we'll touch on at the end of the day, we go from, we basically improve precision quite a bit.
Is it maybe a high-level design question, but is it tend to be task dependent depending on the type of labeling function you're using, depending on the model you're using, whether you're seeing more recall or precision boosts on the end?
Yes.
Yes, all right.
It matters. It is very task dependent. It's very situation dependent. So, okay, great question. So, all right. So this is the pattern matching labeling function section. So, like I said earlier, we can think of labeling functions as just the sort of Bayesian inference type of way where we have some sort of prior defined over our feature space. For instance, here we could define a dictionary of terms that may or may not indicate a true relation. So let's say we're looking at treatment as a keyword. One of the most common sort of things you'll do for detecting these relations is looking at words in between the arguments, right? We saw that in the spouse example, that's where most of the information showed up. So you could imagine like a very common sort of set-based way to look at these things is to just write a one-liner labeling function that looks for terms occurring between the arguments in your sentence. So in this case, you define, there's a typo here, you define like a dictionary. And just look for its intersection with the tokens that occur between. This is a deadly simple, right? This is the same type of thing that's probably more effectively done by regular expression, which we'll look at in just a bit. But this is the basic gist, right? You're looking for words are correlated with the label, with a certain label. All right, so we have made, because that particular pattern is so common, we've basically made a helper class that does it for you automatically, so that you don't have to use, you certainly can, and I encourage you to, but you don't have to rely exclusively on the Snorkel helper functions. We've basically reduced this to more or less defining a dictionary or defining a regular expression and then invoking this one-liner Python to produce your labeling function for you. And we just have two objects. One's called match terms, match regex. They accept 4 possible parameters. One is you assign a unique name. That's going to be mapped to your labeling function. You want a label. That's going to be 1, -1. A search space. That's, am I searching to the left, to the right, in between, the whole sentence? And some window. So if you're searching left and right, maybe you only want to look at the word immediately to the left or immediately to the right or something. You can restrict that by specifying an arbitrary window. So what does this look like if we actually invoke it? Well, we define, again, just a set here. and then we call this match terms. I'm going to name this treatment. I'm going to call this label, it's going to vote true if it sees the word treatment occurs between. Yeah, absolutely. So you can pass in, I don't know if we have this as an attribute. You can definitely do it if you do it manually. I think there may be a helper here. I'd have to check. All right, so what is this code doing here? I've defined a labeling function. I've used this match terms object. I've given it a name. I've passed in a dictionary or a set of terms. It's voting true. I'm defining the space that I'm searching, which is between, and then I'm invoking this function lf, which generates a labeling function. And that's just a one-liner. I get this now. And then I can go and look at some metrics. I want to see how many candidates does this labeling function vote on. And then I want to actually view those candidates. So this coverage applies the labeling function, generates a list of candidates that match that labeling function or are voted on by that labeling function. And then I can put those into my n-gram viewer to examine them. So it looks like this treatment votes on 4.5% approximately of all the candidates in my training set. What set are we operating on? Yeah, so again, the split tells me which set I'm looking at. Set 0 is an unlabeled training data set. Split 1 is a labeled dev set. And then we have another split for test set, but don't look at it. So, all right, yep.
Just in development, it seems like it'd be really handy to know how much you're touching in general across multiple labels. Is it easy to say union get this equivalent coverage view of rule of label function 1, 2, and 3?
Yeah, so you'll, at the end of this notebook, when we run all of our labeling functions, we're like nose to the page view of just one labeling function at the moment. At the very end, when we run all of them, you'll get tons of metrics for everything. So, yeah.
What's the difference between name and terms arguments?
Name is a labeling function has a name, so it'd be like LF treatment, and that's so it's just uniquely in the label matrix. Yeah. Okay. And you'll see if we look here, remember our rule is to look for treat. This carbamazepine, I totally botched that pronunciation, treatment in rat, efficacy, toxicity, blah, blah, blah. And you can see how these shake out. They all should match your criteria. So this is an opportunity to bug check more than anything, is to see if what you intended the labeling function to label is actually being labeled, right? So that's one thing. Am I firing on some right set of candidates? The other question is my intuition right or wrong, right? That's where the dev set sort of can step in. So here, I'm saying I would like to do an error analysis. I want to take my labeling function, apply it to my labeled dev set, and see what my empirical measures are. And then I want to look at those data. And you'll see here, I'm getting fairly low precision. Ignore recall in this setting. It doesn't. It's defined over a smaller set. But basically, I fire true. I catch 14 true cases, but 45 false positive cases. Right. So treatment is there's maybe some signal there, but it's pretty noisy, right? And so it's a very weak labeler. And we can, of course, as I said, walk through and look at what's been labeled. Do you guys see any if you were to look at this immediately, do you see any clues that might tell you how to maybe filter this set or restrict what it's voting on? I would just keep that in the back of your mind. Like if you get a big set, a lot of false positives, if you're looking at the data, think about how you could potentially trim that down in some way. Sorry, what's that?
To go to the next, yeah. Is it possible to get the values, something like here, the p-value? It's possible to also return that.
That's it. So you could define a regular expression. We could do that in the very next labeling function factory. Maybe we'll walk through that to identify a pattern in between, right? And you totally could imagine writing a p-value detector and think about using that object in some way. Totally, yeah. Yeah. Yeah, so that was asked. So you can absolutely do it. Let's just maybe settle that for certain. I don't 100% recall how I implemented. It's not this one. Yeah, so every pattern matching factory, which is just some fancy jargon, but if we were to say, let's go back up to this guy for match terms, we pass in now into trib and we want to do lemmas. And so we're at 4.46%, so nothing really changed when we passed in that. Maybe that's fake.
Well, depending on your limitizer, maybe treat or treat
Exactly.
man.
Yeah. So that's a very good point. Lematizer, it's lematizer dependent.
Yeah.
How well does that do in some scientific lingo? May or may not do well. But that's, if you have a better lematizer, you can use it. We have Spaces lematizer, so. Yeah. Okay. So, regular expression factory. So this is basically the exact same idea as term matching. Instead, we want to capture a pattern, right? And so patterns also you could think of as just matching phrases. I'm going to run this guy. This is simply saying I would like to find negations. This say did not. There are, of course, a bunch of different words that indicate negation. You could think about making that much, much better. I should probably pause and say I've deliberately not given you the greatest labeling functions so that you guys can think about it yourself, about how to write better ones. Basically, we've defined this negation. This would vote -1, which is this is false. And we're looking again in the between. And we want to compute the same metrics. This only fires on 6 cases. But you'll see that every one of them catches what we hope it did not. You'll see things like this, which should start getting you thinking about one of the most helpful sort of weak heuristics you can think of in this setting is just if the arguments are really far apart, that's a pretty good clue that, if you're at the start and you're end of a sentence, maybe they're not related. It's a very high level thing, but it turns out more often than not to be true. And we can actually run and see what it is, and it looks like, we are firing, remember our metrics are flipping here. So our true negatives are 5 and our false negatives are 1, so this is actually a pretty good labeling function that only fires on a small set. Okay. If we wanted to do what was suggested, let's go back up and look at this p-value bit. Where was it? We'll punt on that. But yeah, so that's basically that those two helper functions give you a large space of flexibility for defining term sets that are correlated with true false labels, defining regular expressions to extract stuff you think are correlated, all types of things like that. So you could totally imagine like the p-value bit, maybe that alone doesn't tell you a lot of information about if a label is true or false. But maybe you'd write a Python helper function that could extract that and use it in conjunction with some other domain knowledge to write a slightly more complicated labeling function that does give you, signal one way or the other. All right. So the next big class of labeling functions are distance supervision based. So as I said in the slides, we'll be looking at this comparative toxigenomics database. It essentially has taken a large set of chemical entity pairs that are broken down into 3 categories. Therapy, and the chemical treats the condition. Marker, the chemical is typically present with the condition. And then unspecified, which is unspecified. I don't know what that means. We've defined some helper functions that loads this database and lets you check to see if a candidate is a member of that database. This will take a little bit to load, not a huge amount of time, but just to go and walk through this concretely, let's say we say, the chemical is typically present with the condition. I'm going to say, maybe that's a weak signal that there's some causal thing going on. I'm going to write a labeling function manually that uses these helper functions to check and see if my candidate, which again is a chemical disease pair. Behind the scenes, we've done some normalization so they have canonical IDs so that we can check the database. We've done a lot of cleanup to make that process easier, but conceptually, all it's doing is checking to see if it's a member of this particular subtype of the database. It says, I'm going to vote true if it's in the database. Otherwise, I'm going to vote 0, which is abstain. And we'll vote, and you'll see that in fact, it has, it's not terrible, right? We're basically about 50-50 in terms of right or wrong. So but we have decent coverage, right? So we're labeling a big set. So that should give you like an idea of maybe that's a foundation of a nice big true positive set that you could think about writing labeling functions around to filter out some of those false positives. And we'll talk a little bit about some strategies there in just a second. All right?
So one
yeah.
thing I'm noticing, and maybe this I'm wrong, all these labeling functions are binary. Right?
What's that?
All these labeling functions, they're just binary functions. They cannot return 3 values.
Well, so in this setting where it's binary classification, they do vote, true, false, abstain, right? If it were multinomial, they would vote regarding the number of classes, yeah. Right. Okay. Any questions so far with the stuff we looked over? So we've talked about pattern matching, regular expression-based labeling functions, and then distance supervision ones. These aren't disjoint categories. They are, you can mix and match them to write labeling functions, right? Or add your own custom labeling functions, which is what we'll talk about now. So as I hinted at above, a very good first pass heuristic is, are these entities really far apart in a sentence? How do I do that? Well, in our exercises in the API notebook this morning, we did exactly that. We generate a list of all the tokens that occur between entities, and we just count them, right? If they're above some threshold, which we set for 10, we just did that empirically by looking at stuff. You could pick any number you feel is appropriate. We vote negative. And then we can compute our metrics. And we'll see that this is actually a pretty good labeling function, right? It's way more than it's wrong. And we can think about playing with this number to sort of change how those metrics shake out, which has, affects the number of things we fire on, but there is some trade-off, right? Okay. The template of a custom labeling function is just a simple Python function, right? You can call any candidate API member function you want. You can do whatever you want. It's a black box. You just have to vote at the end. All right. So another strategy that is very useful, these numbers might change depending on how I change stuff, is composing labeling functions. And this is where we get to an idea, again, this very API-like idea of labeling functions, where you say, well, I knew above that my treatment occurring between, had these sort of precision, very, low true positives, high false positives, but maybe I could combine them with another labeling function to filter out some of those false positives and try to, improve its accuracy. And this is just a toy example here of that idea. And again, the numbers might change a little bit. They're right. Okay, got everything in sync. But we'll see that, we've got, we lost 5 true candidates by composing the length, checking if the arguments are too far apart and checking for the word treatment. We lost 5 true candidates, but we cut our false positive rate by 28. Yeah?
So are there any kind of guiding principles you use to decide whether to compose labeling functions yourself or let the generative model kind of combine them on its own?
Yeah, that's an interesting point. So usually the labeling, whatever happens in the labeling functions is invisible, like unknown to the generative model. So my sort of rough guideline is to encode some heuristic, right? Some sort of conceptual category in a labeling function that makes sense. The labeling function not be necessarily adversarial, right? So if it's better than chance after a certain threshold, then you toss it to the generative model to combine it in a smarter way. There are these sort of like mix and match helper functions where you're really, you're sort of defining a weak feature space over something that you want to tag, right, or vote on. In that setting, it tends to be write a couple labeling functions that use helper functions in some way. Yeah. Okay. So that basically is a lightning walkthrough of the 3 big classes of labeling functions that we'll be talking about today, right? So what we'll do now is we'll open it up so that you guys can start playing around and writing your own labeling functions, and we'll walk around and answer questions as needed, but just go ahead and dive in, and then we'll look at cell number, 9 here, which is viewing error buckets. It's in section, like term matching factory section. I think it shows up earlier. These error buckets are your true positives, false positives, true negatives, false negatives. That's just a list of what that labeling function fired on. If you put that list into the n-gram viewer, you can view specific error categories, right? So I'm looking at my true positives. I could just as easily fit in false positives. So that's a way to sort of investigate the labeling function's output. Is we need to have your labeling functions applied and being used to generate a label matrix behind the scenes while we talk about the generative model, which combines all the labeling functions. So hopefully you've been placing all of your LFs in this box. Basically what you want to do is you'll have a name associated with every labeling function. Put them all in a list like this. We'll go ahead and run this. This should be fine. And what we're going to do is this labeler class right here is what actually goes and applies the labeling functions to all of our candidates in our training set and development set. And so now we've spent, the first 30 minutes, an hour or whatever, sort of looking at individual labeling functions. What this is doing is now applying them all, and we're going to start thinking about how do we unify them, explore their aggregate metrics, and see how they interact with each other. This takes a little time, so let's go, go ahead and get everything launched so that you know it's running, and then we can move to the lecture. Is anyone not able to run this stuff?
Just to be clear, you want us to append our functions to that, not replace it.
If you feel that labeling function is of sufficient quality, you can include it. You can include it and remove it later. I think it's whatever you think's most informative. I don't think it hurts to run it the first time just to see how it shakes out. And you see that it takes, not that much time, about a minute to run my simpler labeling functions. You can see that I have this, what does this generate? This generates a label matrix for train and a label matrix for development set. We can then go and look at the LF statistics. These are the labeling function helpers that I used, and then these are the manually generated ones that we put together. And you'll see these are all of the metrics we can compute in the absence of labeled data, right? We can look at their coverage. This covers 4% of the 4.5% of the data. This one covers 1% of the data. We can look at how they conflict with each other and overlap. Sometimes that's not the most informative, so we'll look at our development set, and this will actually break it down into true positives, false positives, and true negatives, and give us an empirical accuracy assessment. So we can see here that just using the word treatment, has a 23% empirical accuracy. That's not particularly great. The negation, the very restricted set, very small set of negation terms, is very highly accurate. That's like 83%. You'll see here when we're using the knowledge base, that's a little over 50%. If you look at the too far apart heuristic, that's almost 76% accurate. And then, of course, if we take treatment and compose it with another labeling function, we move up from 23 to 34, right? And so basically, if you guys could wrap all your labeling functions up, run this notebook end to end, we'll be in a position for when we run the generative model notebook, everything will work out of the box. And if you don't do this part right, the next notebook's going to break. So we'll just try to make sure everything is in order.